Hi everyone, my name is Yash and I'm a student at California State University in Northridge. Today I will talk how AI can help insulin dosing decision in type 1 diabetes care through machine learning prediction, clinical safety rules and large language models via RAG, which will explain the decision. Managing type 1 diabetes require many insulin decisions. Patient need to inject many insulin dose each day. I will start my talk why these decisions are hard, because type 1 diabetes require many insulin dosing decision each day, and this decision can be affected by meal, physiological factors, activity, many other body-related features. Small error while taking this dosing can lead to a severe medical condition for patient. And most of the current system are reactive, and they are not using multimodal data to give a decision. So we ask this question: Can AI prevent and solve this issue while having human in the loop? And we propose this system, which has three main components. Machine learning will predict short-term glucose prediction. Based on that predicted glucose, we will give the recommendation how much insulin it will require. And in final layer, we will explain that recommendation using large language model, which will use retrieval augmented generation. And also, while all of these three modules, we are keeping this thing in mind. We will only give recommendation, but final decision always made by the patient itself, himself or herself. Now let me show you how these each individual component work together as a single pipeline in our system architecture. So starting with the input data, we have multi-model input data that goes to our machine learning pipeline, where we will predicting short-term glucose value. Based on that prediction, we are passing that predicted value to decision engine, which follow the strict clinical rules and clinical safety constraints. Now, that decision engine will generate the output, which we are showing on the dashboard that we have created user interface. And now, if user or patient have any question related to generated decision, they can ask using via chat interference. In last talk, we have Sir mentioned a thing about the prompt injection and having better context, giving better context to the LLM. That's what we are doing here. We are doing prompt augmentation. Prompt augmentation is a technique where we are enhancing a user question or user prompt to certain level so LLM can understand better context. We are sending user question. In addition to that, we are sending output summary, and we have defined a system rule which tells LLM how to act. That augmented prompt will go to the AWS Bedrock, the service that we are using for our foundational model and RAG system. Then that system will retrieve all the required information for explanation from the medical knowledge base that was created by us, which has the authentic medical sources or rules and data. So after retrieval of all the needed information for explanation, large language model will generate the natural language response. We are currently using Claude 3.5 Sonnet model for generating our responses. And based on that natural response, we are again showing into the chat interference. So by doing this, we are incorporating explanation AI. Now I will talk each of, and this is our first prototype where we are very early in our research phase. This is our first prototype system architecture. Now I will discuss each of these three modules in brief, starting with the machine learning model. So we have used multi-model data inputs, which contains four features: continuous glucose value, insulin value, meals value, and activity value, physical activities value. This was recorded from adults who are having type 1 diabetes under real life condition. And this data set was recently published. We are converting that 4 data stream into the 14 engineered features which are physiological and clinical meaningful, which help a machine learning model to improve short-term glucose prediction accuracy. Then we have applied 2 machine learning models, XGBoost and MLP, at 2 horizons, 10-minute prediction and 15-minute prediction. At both horizons, we are getting good accuracy. And XGBoost outperform at both horizon, XGB outperform MLP in accuracy, as you can see right side of the slide. Predicted versus actual glucose traces of patient ID P2301, which is patient 1 of the data set, over the 2 days of time period, x-axis showing time and y-axis showing glucose value. Now we have validated LOPO validation, leave one patient out validation for our machine learning pipeline, where we are holding one patient and training our model on all other patients and testing on that holded patient. And we are repeating this thing until all the patients are covered. Now we have the predicted glucose, which goes to the rule-based insulin recommendation logic, where we were first classified into the 3 risk zone defined by the ADA, American Diabetes Association: hypoglycemia, which is a low blood sugar level, normal range, and hyperglycemia, which is a high blood sugar level. After that, we have predicted glucose level, assigned risk zone, and patient-specific information. Based on that, we are using rules-based insulin logic, which will prevent insulin stacking in body and any unsafe insulin dosing. Finally, system will give the recommendation how much insulin should patient take or should not take based on patient condition. All of this decision are strictly followed by the medical rule and follow medical constraint, medical safety constraint all the time. Now, let me explain you the final layer of our work, which is a LLM, which explains the decision. We are using retrieval augmented generation for explanation. Let me give you an example. When user asks a question, why I am showing 3.4 dose of recommendation, our LLM will use our system prompt, user question, and medical knowledge base that we have created. Using all of these 3, it will generate the natural language response, which can be easily understandable by user or a patient. At the same time, it also it reduces the hallucination due to we are using RAG. And all this medical knowledge that we have stored in medical knowledge base are authentic. In future, we want to add more 2 use cases of LLM. First, LLM for input structuring, where patient give any unstructured input data. We want to convert that unstructured data to the structured data for system logs. Let's say patients enter any medical logs or a food instruction. I had one bread, how much carbs it will calculate it. We want to that natural language response to unstructured format for machine learning purposes and clinical review purposes. And the other use, we want to incorporate LLM as a safety monitoring, where LLM will look a patient log over the time, and it flags the recurrent risk zone, which helpful for clinical review. And all of these 3 use cases, we want to make sure LLM always act as a supporting layer and safety layer, not a decision maker. We always want to decision made by the medical rule-based logic that we have created. Now let me give you a first view, a demo of first prototype that we have created. It is not showing. I'm opening it, but it is not showing over there. It is here. But yeah, I think this might be.
If you exit the slide mode completely.
Okay. Yeah. Yeah.
Just quit PowerPoint.
Yeah. Let me do it from here. So this is the first prototype or this demo that we have created. We have created, let me play the video. We have created 3 clinical scenario for this presentation. We are selecting one scenario. That is hypoglycemia risk, low blood sugar level. We do run analysis using all past information. This machine learning model and logic, insulin logic will give this all information which are showing in this dashboard. Current glucose, predicted glucose, risk zone, and final decision that how much insulin should take or should not take based on patient condition. Now, instead of guessing why this decision was made, we can directly ask our system, that our chatbot, why this decision was made. And it will let us know using all medical knowledge, system prompts, and patient-specific information. It will generate the natural language response, as you can see. And if you have any further question or related to the type 1 diabetes, type 2 diabetes, it also answers that questions here. So the key takeaways from this work, machine learning will predict, rules will decide the recommendation, and large language model will explain. While having all the clinical alignment, which means it should follow the clinical safety rules and clinical rules to make the decision. In future, we want to expand LLM use cases. Also want to incorporate more multimodal data set so we can make it more personalized, and want to plan to add more medical rules and safety constraint to be more to act my system to be more safer and personalized for type 1 diabetes care. Thank you, everyone. And I want to acknowledge CSU Biotech for financially supporting this project through 2025 faculty grant, student research collaboration grant.